Using conduit as equipment grounding has both advantages and disadvantages. Let's consider the pros. Firstly, it's cost-effective. Conduit is often the most economical option for equipment grounding, as it doesn't require additional materials or labor. Secondly, it's convenient. Conduit is readily available and easy to install, making it a practical choice for many applications. Thirdly, it ensures compliance. Conduit grounding is recognized by electrical codes as an acceptable means of grounding equipment. Fourthly, it provides durability. Conduit provides a rugged and durable grounding path, protecting against damage and ensuring the safety of the electrical system. Now let's examine the cons of using conduit as equipment grounds. Firstly, there's limited effectiveness. Conduit grounding is less effective than dedicated grounding conductors, especially in high-frequency applications or where there is significant electrical noise. Secondly, voltage drop can occur. Conduit grounding can introduce voltage drop along the equipment grounding path, potentially affecting the operation of sensitive electrical devices. Thirdly, there's a corrosion risk. Conduit can be susceptible to corrosion, which can compromise its grounding integrity and create a potential hazard. Fourthly, there's required maintenance. Conduit grounding may require periodic inspection and maintenance to ensure its continuity and effectiveness. Several resources provide further information on this topic. One is an article from Electrical Consultants titled Conduit as Equipment Grounding Conductors, a review of code requirements and best practices. Another resource is Using Conduit as Equipment Grounding Conductors, Advantages and Considerations from AE Electric. A third resource is a document from the University of Michigan titled E380 Electrical Safety Grounding Conduit as Grounding Conductor. Lastly, IEEE Standard 142-2007 Recommended Practice for Grounding of Industrial and Commercial Power Systems provides further information. Understanding the pros and cons of using conduit as equipment grounding is crucial for ensuring electrical safety and code compliance. The effectiveness of conduit as an equipment grounding conductor depends on factors such as the type of conduit, the installation practices, and the characteristics of the electrical system. Steel conduit, such as rigid metal conduit, RMC, and electrical metallic tubing, EMT, generally provides a better grounding path than aluminum conduit due to its lower impedance. However, even with steel conduit, it's essential to ensure that all connections are tight and free of corrosion to maintain a low impedance path to ground. The National Electrical Code, NEC, provides specific requirements for using conduit as an equipment grounding conductor. These requirements are primarily found in Article 250. For example, Section 250.118 lists the types of equipment grounding conductors recognized by the NEC, which include metal raceways such as RMC, IMC, and IMT. However, the NEC also emphasizes the importance of ensuring that the impedance of the grounding path is sufficiently low to limit the voltage to ground and facilitate the operation of overcurrent protective devices. In situations where the impedance of the conduit is too high, a supplemental equipment grounding conductor may be required. The effectiveness of conduit grounding can be affected by several factors, including the length of the conduit run, the number of bends in the conduit, and the presence of any discontinuities or corrosion. Longer conduit runs and multiple bends increase the impedance of the grounding path, which can reduce its effectiveness. Corrosion at joints and connections can also significantly increase impedance, compromising the integrity of the grounding system. Proper installation practices are crucial for ensuring the effectiveness of conduit grounding. This includes ensuring that all connections are tight and free of corrosion, using approved fittings and connectors, and avoiding sharp bends in the conduit. It's also important to properly bond the conduit to the equipment being grounded to provide a low impedance path to ground. Regular inspection and maintenance are essential for maintaining the integrity of conduit grounding systems. This includes visually inspecting the conduit for signs of corrosion or damage, checking the tightness of connections, and performing continuity tests to verify the integrity of the grounding path. Any issues identified during inspection should be promptly addressed to prevent potential safety hazards. In some cases, the use of a supplemental equipment grounding conductor may be necessary to ensure adequate grounding performance. This is particularly important in situations where the impedance of the conduit is high, such as in long conduit runs or where there are multiple bends. A supplemental grounding conductor can provide a lower impedance path to ground, improving the overall effectiveness of the grounding system. When using conduit as an equipment grounding conductor, it's important to consider the potential for galvanic corrosion. Galvanic corrosion can occur when dissimilar metals are in contact in the presence of an electrolyte, such as moisture. This can lead to the corrosion of one of the metals, which can compromise the integrity of the grounding system. To prevent galvanic corrosion, it's important to use compatible materials and to isolate dissimilar metals where possible. For example, when connecting steel conduit to aluminum equipment, it's important to use a suitable insulating fitting to prevent direct contact between the two metals. In addition to the NEC, other standards and guidelines provide information on the use of conduit as an equipment grounding conductor. For example, the IEE 142 standard, also known as the Green Book, provides recommendations for grounding industrial and commercial power systems. This standard covers various aspects of grounding, including the use of conduit as an equipment grounding conductor, and provides guidance on how to ensure adequate grounding performance. When evaluating the suitability of conduit as an equipment grounding conductor, it's important to consider the specific requirements of the application. This includes factors such as the voltage and current levels, the type of equipment being grounded, and the environmental conditions. In some cases, a dedicated equipment grounding conductor may be a better option, particularly in critical applications where safety is paramount. Ultimately, the decision of whether to use conduit as an equipment grounding conductor should be based on a thorough evaluation of the specific circumstances and a careful consideration of the relevant codes and standards. Proper design, installation, and maintenance are essential for ensuring the effectiveness and reliability of any grounding system, regardless of whether it uses conduit or a dedicated grounding conductor. The increasing use of sensitive electronic equipment has also led to greater awareness of the importance of effective grounding. Electronic equipment is often more susceptible to damage from voltage transients and electrical noise, making it essential to provide a low impedance path to ground. In these situations, a dedicated equipment grounding conductor may be necessary to ensure adequate protection. Conduit grounding systems should be designed and installed to minimize the risk of electromagnetic interference, EMI. EMI can disrupt the operation of electronic equipment and can even cause damage. By properly grounding the conduit and minimizing the length of unshielded conductors, it's possible to reduce the amount of EMI generated by the electrical system. In summary, using conduit as an equipment grounding conductor can be a cost-effective and convenient option, but it's important to be aware of the potential limitations and to follow proper installation and maintenance practices. A thorough understanding of the relevant codes and standards is essential for ensuring the safety and reliability of the grounding system. Always consult with a qualified electrical professional to determine the best grounding solution for a particular application. Remember to consider all factors, including cost, convenience, effectiveness, and safety, before making a decision. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. In the context of electrical safety, the term grounding refers to connecting electrical circuits and equipment to the earth, which serves as a reference point and provides a path for fault current to flow back to the source. This process is crucial for preventing electrical shock and minimizing the risk of fire or damage to equipment. Equipment grounding, specifically, involves connecting the non-current carrying metal parts of electrical equipment, such as enclosures and frames, to ground. This ensures that if a fault occurs, such as a short circuit between a live conductor and the metal enclosure, the fault current will flow through the grounding path back to the source, causing the overcurrent protective device, such as a circuit breaker or fuse, to trip and energize the circuit. This rapid disconnection of the power supply prevents the metal enclosure from becoming energized, which could pose a serious shock hazard to anyone who comes into contact with it. The National Electrical Code, NEC, provides detailed requirements for equipment grounding to ensure electrical safety. These requirements cover various aspects of grounding, including the types of grounding conductors that are permitted, the methods of connecting grounding conductors, and the sizing of grounding conductors. Compliance with the NEC is essential for ensuring that electrical systems are safe and reliable. In addition to preventing electrical shock, equipment grounding also helps to reduce the risk of fire. When a fault occurs and current flows through the grounding path, the impedance of the grounding path determines the magnitude of the fault current. If the impedance is too high, the fault current may not be high enough to trip the overcurrent protective device, which can allow the fault to persist and potentially lead to overheating and fire. Therefore, it's important to ensure that the grounding path has a low impedance to facilitate the rapid clearing of faults. Equipment grounding also plays a role in protecting sensitive electronic equipment from damage. Voltage transients, such as lightning strikes or switching surges, can cause damage to electronic equipment if they are not properly grounded. A well-designed grounding system can help to divert these transients to ground, protecting the equipment from damage. The design of an effective equipment grounding system requires careful consideration of several factors, including the type of equipment being grounded, the voltage and current levels, the environmental conditions, and the applicable codes and standards. It is important to consult with a qualified electrical professional to ensure that the grounding system is properly designed and installed. The selection of appropriate grounding conductors is also crucial for ensuring the effectiveness of the grounding system. Grounding conductors must be sized according to the requirements of the NEC and must be made of materials that are suitable for the environmental conditions. Copper and aluminum are commonly used as grounding conductors, but other materials may also be used in certain applications. The installation of grounding conductors must be done carefully to ensure that they are properly connected and that the grounding path has a low impedance. Grounding conductors must be securely connected to the equipment being grounded and to the grounding electrode system, which is the connection to the earth. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground water pipes. Regular inspection and maintenance of the equipment grounding system are essential for ensuring its continued effectiveness. Grounding connections should be checked periodically to ensure that they are tight and free of corrosion. Grounding conductors should also be inspected for damage or deterioration. Any issues identified during inspection should be promptly addressed to prevent potential safety hazards. In summary, equipment grounding is a critical aspect of electrical safety. It helps to prevent electrical shock, reduce the risk of fire, and protect sensitive electronic equipment from damage. A well-designed and properly installed equipment grounding system is essential for ensuring the safety and reliability of electrical systems. Always consult with a qualified electrical professional for assistance with the design and installation of equipment grounding systems.